Let's talk about solids. The particles in a liquid are relatively free to move. They can slide past one another, and we call that property flow. Solid particles are not free to move. Solid particles can only vibrate around fixed points rather than slide past one another from place to place. So here's a solid particle diagram here. We see the particles vibrating in fixed position here. They are packed tightly. Another way of saying that is they have a crystalline formation. They have a highly organized pattern, and they do not flow. Like we said, they do not slide past one another like a liquid or a gas can. Because of this, they also don't take the shape of the container that they're in. So they have a fixed volume and a fixed shape. Like liquids, solids are a condensed state of matter. Increasing the pressure does not affect their volume. So here's my solid once again, and as I pressurize them and push down, we see that nothing changed. They're still moving, but they didn't change shape, they didn't decrease in volume. Um, so like I said, fixed volume, fixed shape for solids. So when a solid is heated, the particles vibrate more rapidly as the kinetic energy of the particles increases. Eventually, those vibrations become so strong that they will overcome the intermolecular forces of attraction that are holding them together, and the solid will melt into a liquid. The melting point can be reversed by cooling the liquid so that it freezes. If we take away that kinetic energy, we'll take away the motion of the particles that's allowing them to flow, and that intermolecular forces will pick back up and they will reform that crystalline repeating pattern that is characteristic of solids. So the temperature at which remains constant until all the liquid has solidified at 1 atmosphere is called the freezing point of the liquid. The heat of solidification is the amount of heat needed to change 1 gram of liquid water at STP to 1 gram of solid at the same conditions. The heat of solidification is 334 joules. Like the heat of vaporization or condensation, this isn't a number you need to memorize. This is on your reference table right on the very first page. You just are going to need to know when to use it for certain math problems that we'll learn in later chapters. The amount of heat needed to change a unit mass of a substance from a solid to a liquid, in other words, saying the amount of heat we need to add to melt something at STP, is called the heat of fusion. For ice, it is also 334 joules. It just depends on whether we're adding 334 joules to melt something or taking away 334 joules to solidify or freeze something. We can see this on a heating curve here. So this is a typical heating curve for any substance. We can pretend it's water. Um, on the slanted part of the lines, we have our pure states of matter. So our first leg here of the curve from A to B, this slant here, the substance is a solid, and we're heating the solid for, looks to be about 2.5 minutes, and it's going from 0 degrees Celsius to about 50 degrees Celsius. And then we reach the flat line part of the graph. We'll call this leg BC here. The graph is leveling off here. That is the heat of fusion. So we've added enough energy to start turning this solid into a liquid at this temperature. I guess it wouldn't be water, because water wouldn't melt at 50 degrees Celsius. It would melt far, before that, but that's okay. So the flatline parts are the transitions where we are, in this case, melting, and it is also where the heat of fusion would be located. Then we reach another slanted part, leg CD of this graph here. This would be when all of the melting is done. Well, by the time we get to C, now we are pure liquid, and the liquid is getting hotter over the next couple of minutes until we reach point D, and that would be at 100 degrees here. At point D here, we are starting to vaporize or boil the liquid. That is where we would reach the heat of vaporization. We've added enough energy to keep the temperature constant while we are transitioning to a gas state. By the time we get to E, we are 100% gas, and now the gas is just being heated up from E to F here. So this is a heating curve. You need to know how to read one basically. You need to be able to identify where certain things are on the curve, like where the solid states of matter are and where the transitions are. You should also have an idea of what's happening to the kinetic and potential energy on these curves, and we'll talk more about that in class. But if temperature is kinetic energy, as we go up this curve, kinetic energy is increasing. But if we flatline here, kinetic energy is flatlining and staying the same. If temperature is not changing from B to C or D to E, kinetic energy is not changing. But we're adding energy throughout this entire 17 minutes in this heating curve. So where does that extra energy go? Well, it gets added to its stored potential energy. So potential energy increases on the flatline parts. Kinetic energy increases on the slanted line parts. We could have the opposite of this. This is called a cooling curve, where we would just be going downhill here. So we're starting at a super hot gas from A to B, and we're condensing to a liquid during BC. That would be the heat of condensation. And then by the time we get to C, we've condensed to a liquid, and we're just cooling the liquid down from C to D. And then from D to E, we are freezing. We've reached the heat of solidification, and we're freezing the liquid throughout the process, throughout this line D to E. By the time we get to E, we're 100% solid, and we're just cooling down to solid for the last couple of minutes. So the idea is the same. The states of matter are always on the slanted lines. It's just we're starting with a gas and cooling to a solid rather than starting with a solid and heating to a gas. These things will change, so we're condensing instead of vaporizing, and we're solidifying instead of reaching the heat of fusion. But the idea is just the same. So in summary here, you should know the basic properties of solids, as well as how they transition to and from different states of matter. You also need to be able to interpret heating and cooling curves and be able to identify where the pure states of matter are and the phase transitions are on the curve. And we'll be practicing more of this in class. So if you have any questions on this or anything else, please let me know.